There are 3 pairs of orthogonal directions in this room or in the universe. And within a pair, each direction is anti-parallel to the other. So anti-parallel just means the opposite direction. So maybe point with me. So we're going to point north, I think, and south. North, south, west, east, up, down. So let's do it again. We'll do North Pole, Mexico. We'll do Vancouver, Halifax, and we'll do heaven, hell. Okay, all kinds of places you might go. Okay, so we're talking about vectors. A vector is a quantity that is, a scalar is a quantity that's described by a single number. And when you have a calculator, you're always typing scalars into your calculator, at least my calculator. But a vector is something that has both a magnitude and a direction. And so a geometric representation of a vector is you just draw an arrow on a page, on your diagram. And the idea is that sometimes the tail of the arrow is a place where you make the measurement, and then you just sort of draw the tip as the pointy end off that direction. You can name the vector. Sometimes I put a little vector sign over, like a little arrow sign, on top of the symbol to remind me that it's a vector and not a scalar. Because they're so different, right? So if you're going to write V without the little arrow on top, I often take that to mean the absolute value or the magnitude of the vector V. And if I put a little vector sign on it, then I have to remember in my head that it's not just a number, it's not just a magnitude, it's also a direction. So the small arrow, like there's things like position is a vector, velocity is a vector, acceleration is a vector. Okay. All right. So then there's vector math, which is not the same as regular math. You have to define it. And so the mathematicians have defined how to do this stuff. What we can do is if you're adding 2 vectors, maybe E plus D, there's E and there's D. So there it is, E and D. You can use these geometric methods. One is that you can just sort of shift, this is what your textbook does, it shifts one of the vectors' tail over to the tip of the other one, and then the sum is this diagonal here. And then parallelogram rule is just another way of doing the exact same thing. And I asked actually people if they would use this pre-class, this Fed animation. 112 of you did it. It looks kind of like this. Basically, it just shows how to add 2 vectors. I'm adding B plus A. And if you change around B or change around A, the S there is the sum. S equals B plus A. And if they're in opposite directions, the sum goes away. If you add a vector to its opposite, I guess, then you get 0. I don't know if they're together, then you get something that's kind of like in the same direction. Sort of see if they're perpendicular, you're going to get something that's along some sort of diagonal. Here's a situation where the y component of A is negative of, the opposite of the y component of B, and so the sum ends up being right along the x-axis there. It's fun to play around with that. Okay. I had some physicsy questions on here. Can we add vectors in any order when calculating them? So it turns out that vector addition is what the mathematicians call commutative, which means you can just flip it around. So it means that A plus B equals B plus A. Doesn't matter what order you add them in. Can we multiply or divide 2 vectors? Well, you can, I don't know about divide, but you can certainly do a dot product or a cross product. So if you have 2 vectors, we're not going to we don't do this in this chapter, but later on in the semester, when we talk about work, for example, work is the dot product of the force vector times the displacement vector. It turns out to be commutative, and you get a scalar, which is work. And then later on, we get to torque. Torque turns out to be the cross product of like the position away from, as mentioned, the displacement from where you apply the force to where it can rotate, and the force. So you do R cross F, and you get torque, this new torque vector, which is perpendicular to those two vectors. And the vector cross products are not commutative. It matters what order you do. So we do R cross F for torque. But that's kind of a little advanced. Can you go over acceleration, how it's negative versus positive? So simple is that you have to define a coordinate system. Or maybe you were, I don't know, told a coordinate system, but once you define your XY axis, if you define y to be up, meaning towards heaven, that direction, then the acceleration due to gravity is negative 9.8 meters per second squared. If you define y plus y to be down, then the acceleration due to gravity is plus 9.8 meters per second squared, which I think is what I did on that falling water balloon problem. I don't know if you noticed that. I sort of defined plus y to be down. You always use radians to solve. So radian is another way of measuring angle, and I'm not really using that right now. I'm usually using degrees for these problems, and I have my calculator set to degrees mode. Later on, once you get into like simple harmonic motion or something, we might try using radians, but I just like to use degrees, I guess. I guess radians are technically a little better, but I just like using degrees. So. Okay, what else was there? There was, should we consider air resistance in most of the cases? So the answer is most of the time, no. And in fact, if you look at assignment 2, if you're looking ahead, it says right there somewhere at the very top, for all questions, please assume air resistance is negligible unless otherwise stated. So the word negligible means you just ignore it. You can neglect it, I guess, and not just pretend that things are moving around without any air resistance. Because that's the way to solve problems in physics. You make simplifications, but keep in mind that you've done this assumption. How are we doing? Okay, I want to maybe do a quick example, and then we'll do it on the top hat. So distance versus displacement. So from High Park, you ride your bike 6 kilometers east on Bloor Street, and then 5 kilometers north on Yonge Street. We can sort of draw it if we want to draw a top view, okay? So I guess what I did in the beach ball thing is I drew a side view. Well, let's draw a bird's eye view, northeast, west, south. You go this way, 6 kilometers. That's one vector, I guess, and then another, so this is like R1, maybe, or something, and the R2. And then I can just say the magnitudes of these are 5 kilometers and 6 kilometers. So the little absolute value signs are telling you what the magnitudes are. So what is the distance you traveled? Well, that's kind of simple. It's just 6 plus 5, 11 kilometers. And if I had an odometer or something on my bicycle that just showed how far it rolled, it would say 11 kilometers. But the question is, what is your displacement? Well, your displacement vector is here. So we would say that R1 plus R2 in the vector sense is equal to d, the displacement vector. And it turns out that the magnitude of the displacement is going to be the square root of 6 squared plus 5 squared. So you're going to get 7.8 kilometers. And then, that's supposed to be a kilometer. And then you're going to need a little angle to find theta there. The tangent of theta is equal to 5 divided by 6, 5 kilometers over 6 kilometers. So you can do tan to the minus 1. So hopefully you can find the tan to the minus 1 button on your calculator, or arctan or something like that. And you get that theta is equal to 40 degrees, something like that. So then you would say that this displacement vector, wait, this should say, why am I screwing things up so badly? Sorry about that. I'm trying to find the magnitude of the displacement, not R1. The magnitude of R1 is just 6. We need to give you guys things to throw at me. Yes?
Or don't we need a direction for theta as well?
We need a direction for theta as well. So theta, I just drew it on the diagram. So I would say, I could say something like d is equal to 7.8 kilometers, and then I might say 40 degrees north of east or something like that. So that would be how you define it, or just refer to the diagram or something. So this is, final answer. Like that. Sound good? So I've gone from east, gone up north ways, or whatever, counterclockwise, 40 degrees. Can you add a scalar to a vector? You can't. Okay? A scalar and a vector are two different things. It's like adding apples and oranges or something. Like you can't do it. Can you multiply a vector by a scalar? Yes, this you can do. And the rule is you just take the magnitude and multiply it by that scalar. Or you could multiply both of the components by that scalar. Or the other, I guess the second rule there is if you multiply the magnitude by the scalar, if the scalar you multiply is negative, then you have to remember to flip the direction of the vector 180 degrees. So we can do another, this would be a trickier one. Oh, it has given a timer. So I'll increase that. Okay. So, oh wait, I'll get there in a sec. So when a vector is multiplied by a scalar, the result is parallel or anti-parallel to the original vector, whose magnitude equals the product of the magnitude of the original vector and the magnitude of the scalar. So there's some examples here where you've got lowercase c, which is a scalar, times a. So it's just going to stretch it. But if you multiply by a negative 2 or something, then you make the magnitude twice as much, but you flip the direction. Vector components. So all this tip-to-tail rule stuff turns out to be a nice way of checking concepts, but the real way of adding vectors is just use, and subtracting vectors is just use components. It's way, way easier. And there's something called the unit vectors I and j. So I hat, guess with a little hat on it, means it's a vector with a length 1 that's going in the x direction, and j hat is a vector of length 1 that's going in the y direction. And we can say that if you have any vector, it's got an x component, which is a scalar, times I hat gives you like this horizontal vector, and then the y component, which is a scalar, times j hat gives you this vertical component. And when you add these two vectors, you get, when you add the two component vectors, you get the original vector. And components, luckily, add just like scalars, and you can just do it on your calculator. So let me give you an example. What is the magnitude of the vector c, which is 2a minus 3b? So trying to do this the geometric way with tip to tail and all this stuff is going to be just a major headache. But I can do it with components in about a minute, and I'll show you how it goes, and it's not bad at all. So the first thing I do is find the components. So like for b, you can kind of see that this is like your bx, and this is your b sub y. So I would say that b sub x is negative 2, and b sub y is plus 4. Those are the components. I don't know what the units are. Maybe they're meters. It doesn't actually say the units. And then a, same sort of thing. You've got here, this is going to be your ay, which is negative 3, and then your ax. This one I put here is your ax. It's also negative 3. So ax equals negative 3, ay equals negative 3. And then what you do here is this equation becomes two equations. You just say that cx is equal to 2ax minus 3bx, and cy is equal to 2ay minus 3by. So you just take away the little arrows on top of the vector signs and replace them with either a subscript x or a subscript y. And that's all you need to do. And then it becomes very, very easy. And so what you'll end up with is the components, the x and y components of c, and then if you want, you can recreate c with those components. Pythagoras and the 10 to the minus 1 thing. Ready? Should we do it? So let's start with the x component. You'll just say that c sub x is equal to 2 times a sub x, which was minus 3, minus 3 times b sub x, which was plus 4. Oh, sorry, it was minus 2. There we go. Yeah, so I plugged in the bx and the ax, and I get c sub x is equal to negative 6 minus the minus, so plus 6 is 0 actually. And then the y component, I guess that's handy. C sub y is going to be 2 times a sub y. Oh, and again, there's a nice typo here. Wrong. I meant to say, apologies, a sub y is negative 3. It's never good when I make mistakes, but they're unintentional, I promise. So 2 times a sub y, which is negative 3, minus 3 times b sub y, which is plus 4. So I get negative 6 minus 12, I get negative 18. And again, I don't know the units. So now we have the components of c, so we can, I guess we can try to draw it, but it's some vector which goes down here, c, it goes down to 18. Minus 18. So I would just say that, what is the magnitude of the vector? So the magnitude of the vector c is going to be equal to the square root of cx squared plus cy squared. This is important to know this method for your assignment 2, I think, because there's a question just like this. It's 0 squared plus negative 18 squared. And you get magnitude of c is equal to 18. Try to grab my attention somehow. Yeah. So basically, yeah, if something is flying through the air, it tends to have sort of a parabolic trajectory. So it's made up of 2 independent motions. It's uniform motion at a constant velocity in the horizontal direction. So these blue arrows, so the purple arrows is really what the ball is doing. And then the blue and orange arrows here are the x and y components of the velocity at each moment. And what's interesting is that these blue arrows are always the same. They never change. And that is because a sub x is equal to 0. It's not accelerating in the x direction. It just continues going. Assuming no air resistance, it's always going to the right at that same vx. And then what happens with the orange arrows is that they always change by the same amount each second. So it decreases by this negative 9.8 meters per second every second. So it gets to a point here where this is v sub y equals 0 at the top, and then it becomes negative. And then what's interesting here is that at this moment, v sub y is negative v0y. Once there's sort of a symmetry here. It's gone up a certain distance, come down the same distance, so it's spent the same amount of time stopping as it has speeding up again, so it ends up with the same magnitude of the initial speed, but now it's going down. But with that same x velocity, if you think about the direction of the velocity, it's now flipped. So whatever the initial theta was above the horizontal, now that's the theta below the horizontal. If you think about relative motion, I don't know if you've ever done this, but if you are in a car and you're driving along the highway at 120 kilometers an hour or something, and you're in the back seat, for example, you can still juggle. You can throw a ball up, and then it comes down. But if you think about what the ball is doing, it's doing this big path. So that's relative velocity. So relative to the car, I'm at rest, and the ball goes up and goes down. Relative to the ground, so this is somebody throwing the ball, catching it. If she's on rollerblades and going along at a constant velocity, then in her frame it's the same experience, but from our reference frame, there's this constant x component of velocity that gets added to it. And that's what this parabolic motion looks like. There's a bunch of equations in your textbook that kind of look like this. There's the horizontal motion, which is just the acceleration is 0, and then you've basically just got one equation, which is that x equals x0 plus v0x times t. They just say vx times t, but that's really the initial, I think it's just because it's constant, right? So vx equals v0x. So I might write v0x in this equation sometimes because they're all the same. So that's the simple part. And then for the y component of projectile motion, there's all these same equations. It's the equations from chapter 2 on constant acceleration, which is in the y component. You've got a tennis ball launcher down here. I'm going to put maybe the x-axis this way and the y-axis this way. And then there's some initial velocity, v0. And it's maybe aimed at some angle above the horizontal. And there's a laser pointer which is shooting in a straight line up at this poor little guy up here, the monkey. And so he's at some position x, right? Some final position. So what you do is you break the initial velocity into components. Into its components. That's how you solve a lot of these problems. And the way I do it is I make a right angle triangle. So this velocity, I just draw it over here. This is v0. Here's your theta. And then this is a right angle, and this is v0 in the y direction, and this is v0 in the x direction. And then, do you remember SOHCAHTOA kind of thing? So, let's write this over here. SOHCAHTOA. It means that the sine of this angle theta is equal to the opposite, which is v0y, divided by the hypotenuse, which is v0. And you can solve that out for v0y. v0y is equal to v0 times sine of theta. And then similarly, cosine of theta is adjacent over hypotenuse. So the adjacent is v0x divided by the hypotenuse is v0. So then again, solve for v0x and you get v0 times cosine of theta. So that's your first step. Okay. Next step is, let's start, I guess, with the x component of the motion, because it's the easiest with x motion. Because there's only one equation for it. It's equation in your chapter 3, it's called 3.34. It's just that x is equal to x0 plus v0x times t. And I'll just say that this is the origin right here. So x0 comma y0 is equal to 0, 0. I'm just defining the initial position of the tennis ball to be the origin. So it goes up some distance y, the height of the monkey, I guess, and then, or some distance, and then it goes horizontally a distance x, or displacement, I guess, x. Okay, and then, so this one equals 0, and you get that x is equal to v0x times t, and which is actually v0, don't forget, cos theta times t. We can solve for t, and you get that t is equal to x divided by v0 cosine theta. And then we can use the y motion, in which we don't care about the final speed. We care about Vy final. So if we don't care about Vy final, we can use equation 3.39, which is that y is equal to y0 plus v0y times t minus 1/2 gt squared. And so what we can do, if we write that out, we could say that y is equal to v0 times sine theta times t. Remember, y0 is 0, minus 1/2 gt squared. But we can take this value of t that we got from the x component, and we can plug it in to the y component. So that's a big trick. It comes up a lot in these two-dimensional motion questions, is that there's time in all the x stuff, and there's time in all the y stuff, and it's the same. So you can solve for time using one of the components and then plug it into the other component. So then it looks like this. Y is equal to v0 times sine theta times x divided by v0 cos theta minus 1/2 gt squared. And then there's this thing that it's y is equal to x. I think the v0's cancel. There's v0 on the top and the bottom of that thing. So you get, it's x tan theta, because tan theta is sine over cos, minus 1/2 gt squared. So y is equal to x tan theta. You think of the displacement here. If this is y and this is x, and this is theta, then tan theta equals y over x. Basically, this is the straight line path. It's the path of the laser beam, actually. So this, I guess, delta y is negative 1/2 gt squared is the distance that the tennis ball falls below. The ball falls below the straight line path. So, and then there's another thing, which is that if you release something from rest, it falls a distance 1/2 gt squared. So you got two things happening. One is that the tennis ball is falling below the straight line path at by this distance 1/2 gt squared. And then the other thing is that for the entire duration of the flight here, the monkey is falling at 1/2 gt squared, and then so they fall this, so they end up at exactly the same y height whenever it gets here. Unless, of course, I guess the tennis ball hits the floor first or something. But as long as it's still in the air, the monkey did the absolute worst thing he could do by letting go at the exact moment that the tennis ball was became a projectile. Okay. An airplane is delivering food to a small island. It flies 100 meters above the ground at a speed of 160 meters per second. So what you've got is the water and an island, and I think there's an airplane up here, which is going along. And it's got some speed. V is 160 meters per second. And it's at some height of 100 meters. And then I think what goes on is that this parcel is supposed to fall down and hit the island or something. I think that's the basic idea. And what we're going to do, I like to write down things like, let's assume no air resistance. Which is kind of a ridiculous thing. I mean, how can you fly an airplane with no air resistance? But we can't solve the problem if we can include air resistance. So if we're going to get an answer, we have to just neglect it. I don't know, maybe it's a very small, heavy package or something like that. So let's assume we can do that. And then I think the idea is that they kind of drop this package of food like from rest relative to the airplane, if that makes sense. So whatever velocity the airplane has, this 160 meters per second, that's horizontal, if they drop the food, the initial velocity of the food will actually be that 160 meters per second. If you can picture that. So I would say V initial of the food is equal to 160 meters per second, and V0y is equal to 0. This is, I guess, if the food is just dropped from the airplane. It's not super obvious that this is true, but that's what I'm going to kind of assume as I'm setting this up. If they were to throw it down or something, you might get a different thing, but if you just release it. So what are we trying to do here? I think we actually don't care, again, about the velocity, the final velocity of the food. Final V of the food. So my guess is we're probably going to be using that equation 3.39 with the 1/2 at squared. What we need here is x, this distance right here, x. Distance, just sort of weird, in horizontal direction. So my strategy, I haven't done much yet, except just talk about what I'm going to do, is I'm going to use the y motion to find the time that it would take to drop that distance. Time, it's sort of like the bullet problem of falling. Because the time of falling only depends on that y component of the motion. And then I can use the x motion to find the distance, the horizontal distance it travels. So equation 3.39 says that y is equal to y0, I didn't define my origin, plus v0 y times t minus 1/2 gt squared. So why don't I do this? I'll put the origin up at the beginning. So this is y and this is x. Origin. So what this means is that y0 is equal to actually 100 meters. Oops. No, wrong. y0 is equal to 0, and then y final is negative 100 meters. Maybe that's not the best way I could have done it. I could have defined the origin to be just below the plane there, and then y initial would have been plus 100. But let's do it this way. Okay, so we need to solve this for t, which is not a good thing because it's a quadratic equation. Oh, no, it's okay because v0 y equals 0, so it's an equation that has a square in it. But it's not a quadratic equation, so we're okay. So it's going to look like this. Y minus y0 is equal to negative 1/2 gt squared. So we can solve that. You times by negative 2, you get y0 minus y times 2 is equal to gt squared. So t is equal to, I think it's the square root of 2 times y0 minus y divided by g. And then we've got the x motion. There's only one equation really for the x motion. It's just that x is equal to x0 plus v0x times t. So, and this is 0. So x is equal to, and we're going to take the time from this one and plug it in to the x component. So we've just got v0 times the square root of 2 times y0 minus y divided by g. So it's 160 times the square root of 2 times y0 minus 100. I think that just ends up being positive 100, divided by 9.8. And x equals 723 meters. It should be 723 meters in front of the island before you drop them. This one is, what angle should you throw a ball so that it travels the longest horizontal distance, assuming you throw it with the same initial speed? So I've done this down at the Credit River. I don't know where my tennis ball went. I've lost it. But I'm trying to throw it across the river. And it's like, what angle should I throw it to get it to go the farthest? So I've got some initial launch angle. And there's a trig identity here, which is sine 2 theta equals 2 sine theta cos theta. So what I'm going to do is, here we've got some initial velocity, v0. It's at some angle theta above the horizontal. It goes up, and then comes down. And it goes some distance x, and we're trying to maximize x. So maximize the range or something like that. So I would say that it spends like half the time going up and then half the time going down, assuming that it doesn't change its whole height. It lands at the same vertical position that it was launched from, half the time going down. So I can kind of say, like, want t a half or something, and t a half, and then t equals t a half plus t a half or something like that. You get it? So I would say that up here, this is when Vy equals 0 after that half. So Vy is equal to V0y minus g times t. That's one of those equations from the previous slide. Remember which one? Times t a half. That's when it's going to stop. And again, from our whole SOHCAHTOA thing, it's kind of crazy here. Remember, this is V0y, this is V0x, this is your theta, this is V0. So if you do all that stuff we did before, it's 0 is equal to V0 sine theta minus gt a half. You solve it out, you get t for half the way is equal to V0 over g times sine theta. And then so equals 2. The time for the whole path is 2 times t a half, so the time for the whole path is equal to 2 V0 over g times sine theta. And now we use the x component, which is the distance it travels is x0 plus V0x times t. This is 0, we'll say. So x is equal to V0 cos theta, is that component, times this whole big thingy. So I've got 2 V0 over g times sine theta. So it's equal to, there's a V0 squared, there's an over g, and then it's times 2 times sine theta times cos theta. That's the distance it travels. But we can use this fancy trig identity, which I found in the cover of my calculus book. They have all these like cool things that are always true. So I can just take this, plug it in here, and I can say that x is equal to some number, V0 squared over g, assuming you've got some launch speed set by the pressure, times sine of 2 theta. And then if you think about some like sine of 2 theta versus theta, sine looks like this, right? So this, versus 2 theta, this happens to have a maximum at sine theta, sine alpha or something, has a max at alpha equals 90 degrees. So I would say that sine 2 alpha, 2 theta, has a max at theta equals 45 degrees. So that means, assuming that g is constant and v0 squared is constant, the sine 2 theta should max out at 45 degrees. So that's the angle you want to try to throw something if you want it to go the farthest distance. This is a special device where he puts 2 balls, and when I hold it up like this, one ball gets launched sideways, exactly horizontally, and the other ball just gets dropped. Okay, see it? Idea being that these velocities are independent. The y motion, you solve that out, that's due to gravity, and then the x motion is independent from the y motion. These are these equations, horizontal motion, vertical motion. Somebody asked, actually, do we use the negative 1/2 gt squared when the acceleration is negative, and 1/2 plus 1/2 gt squared when the acceleration is positive? That's a great question. That's pretty much right. So if you define plus y to be up, which is your choice, I guess, then you use this one, the negative 1/2 gt squared. And the way I kind of remember that is that if plus y is up, then gravity pulls things down, right? So it's trying to make y like more negative. But if you define plus y to be down, then you use the plus 1/2 gt squared in this equation to change to plus, because then gravity's trying to make things more positive. So let's just work this out. Sometimes when you do the actual numbers, maybe it makes a little more sense. But let's put here is y is up, plus y is up. And then we've got something with some initial velocity in the x direction is plus 5.0 meters per second. And it's at a 1 meter high table. So I would say, if this is maybe the origin, then I would say that x0 is equal to 0 and y0 is equal to 1 meter, because it's launched at 1 meter above. And it's going to go, and it's going to hit the ground somewhere over here. So it's going to go some distance, x, which I think is what we're trying to find. No, apply the equations of motion, find how long before the marble hits the ground, and where it hits the ground. So we need t, and x, and how fast is it going just before it hits the ground. So put a question mark there. And also, just before it hits the ground, what's v? Okay, so we know that a sub y, I'll call it, is negative g, because we defined plus y to be up. A sub x equals 0. We can use equation 3.34, which is that x is equal to x0 plus v0x times t. So x just equals 5 times t. So that's a really easy equation to have because there is no acceleration in the x direction. Then we can use equation 3.39 to say that y is equal to y0 plus v0y times t minus 1/2 gt squared. Now this looks like a quadratic equation, but what I didn't put here is that v0y is equal to 0, meaning that that initial velocity is exactly horizontal. There's no y component in the setup, but that means that's 0. So you'd say that y is equal to 1 minus, I guess, 9.8 over 2 times t squared. And that equals 0 when it hits the ground. So we can solve for time. I guess you get that t squared is equal to something like 1 over 4.9. And you get t is equal to 0.452 seconds. And so then you could use maybe x is equal to 5t. So it's 5 times 0.452. Remember we got that from before. So x is equal to 2.26 meters. That's how far it goes. And then vy is equal to v0 y minus gt. That's 0, so it's just negative 9.8 times 0.452. So vy is negative 4.43 meters per second. And also I would say that v, at final, is going to be 4.43 squared plus whatever 5 is, right? 5 squared. Square root of all that. And I guess the other thing we could have done is just drop the ball. The marble is dropped from rest from a height of 1 meter, v0 equals 0. It goes down, we could define plus y is equal to 1 meter. A is equal to 9.8 meters per second squared. Use equation 3.39. Y is equal to v0t plus 1/2 a t squared. I've defined plus y to be down now, so y is equal to 1/2 gt squared. So t squared is equal to 2 over g. Anyway, you get t equals 0.452 seconds, which was the same as it was for the ball going sideways, 0.452 seconds. Okay, so let's talk a little bit about relative motion, which is our last thing. And I'm going to start with relative position. Basic idea with relative position is that you can define RCB as like a displacement. It's the position of C relative to B. This is just this notation that I introduced in that pre-class video this morning. RCA is the position of C relative to A, and RAB, sorry for the handwriting, is the position of A relative to B. And if we take time derivatives of all these, we get these velocities that we talked about last time. Basically, relative velocities are just I guess it's the time derivatives, but it's the VCA, I call that the velocity of C relative to A, VCB, the velocity of C relative to B, and VAB, the velocity of, if you have reference frames, I guess, of A to B. And there's this transformation that looks like that, and that's known as the Galilean transformation of velocity. One interesting thing, if I am moving, am I staying still according to my own reference frame? So I think that's kind of a cool thing is VA or something like that. Velocity of A relative to A is 0. You're always perfectly still in your own reference frame. Could you explain and clarify relative velocity to classical relative velocity? Something about 1% the speed of light. So basically what we're studying in this course is called classical relativity. It was discovered by Galileo a long time ago, or written down correctly by Galileo. It works really well as long as your speeds are much less than the speed of light. The speed of light being 300,000 kilometers per second. So if you start going that fast, then these don't actually work, because there's a rule in physics, you can't go faster than the speed of light, and you can't even really get to the speed of light. Only light goes at the speed of light. And so we call any speeds that are some large fraction of the speed of light, we call those relativistic speeds. And for those speeds, you can't use Newton's laws, really. But so we're going to keep things much slower than the speed of light. And then I kind of noted this cancellation. The inner subscripts here, if you add the two vectors on the right, they kind of disappear. That's my little way of remembering just how this works. And the other thing is that the velocity of 1 relative to 2 is the opposite direction, basically the opposite vector of the velocity of 2 relative to 1. I think that's sort of what you're pointing out there, is that as you're moving, if you move north relative to a tree, then you would say the tree is moving south relative to you. Same speed. Let's do a couple examples. Like a passenger walks towards the front of the train at 5 meters per second. The train's moving at 36 meters per second. What's the speed of the passenger relative to the ground? So that's pretty straightforward one. You've got, I would call it, let's use that notation though, VPT is equal to plus 5 meters per second. I'll define plus x to be towards the right. V of the train relative to the ground is plus 36 meters per second, and we need the velocity of the passenger relative to the ground. It's going to be velocity of the passenger relative to the train plus the velocity of the train relative to the ground, and we got just 5 plus 36, so you get 41 meters per second, and the plus means it's also going to the right. Let's do one that's sort of more in 2D here. Car A is traveling at 25 meters per second, so I'm going to draw a little intersection here of Bloor and Kiel, where this is Bloor, and this is like up here is Kiel. I kind of live a little near here. And you've got car A, which is, I guess I should draw the compass wheel here. This is never eat shredded wheat. Car A is going this way, east, at 25 meters per second. So VA relative to the ground is 25 meters per second. And here's car B is moving north. VB relative to the ground is, it says 15.8 meters per second. And I might define here, let's define plus y to be the north direction and plus x to be the east direction, because we're going to use components. It's asking, just before these two cars collide, what is the velocity of car A relative to car B? So unfortunately, this is about a car accident, but what kind of matters, I guess, if you're in car B, it's not the 25 meters per second the car A is going, it's the relative speed that it's going, relative to you. Because again, car B is always at rest relative to car B. So the answer is, you're going to use, let's use VAB is equal to VAG plus VGB to make those G's cancel. It's a bit weird. Also, VGB equals negative VGB. So what this means is that VAB, which is what you're trying to find, is equal to VAG minus VBG. These are the two numbers that you're getting. So sometimes you have to use this equation and flip things around according to the data you have. So then I'm going to use components. There's an x component and there's a y component. VAG is plus 25 meters per second in the x direction and 0 in the y direction. VGB is 0 in the x direction and negative 15.8 meters per second. That's the velocity of the ground relative to to car B. So basically, I just take the 25 and in the x direction and minus 15.8 in the y direction, and I say that VAB, absolute value, is equal to the square root of 25 squared plus 15.8 squared. So I get 29.6 meters per second. And the other thing is that if this is your theta, and this is your velocity AB, because it's coming at you at that kind of angle, you can get theta is 10 to the minus 1 of 15.8 divided by 25. And you get 32.3 degrees. So you just say that the velocity of car A relative to car B is 29.6 meters per second, and it's 32 degrees south of east. That's what kind of matters if you're in car B. Okay, hopefully you kind of recognize that soft tennis ball is dropped onto a hard floor, a height of 1.5 meters, and rebounds to a height of 1.1 meters. So part A, I mean, there's a lot of ways of doing this, but I would say that V0 equals 0, and maybe Y0 is 1.5 meters. And then it goes down so that Y final is 0. This is just if it hits the ground. Right? This is the floor. And let's define plus y is up. So what that means is that the acceleration in the y direction is negative g. So let's use equation 3.40. You get that vy squared is equal to v0y squared minus 2g times y minus y0. Again, because I've defined plus y to be up, the acceleration is negative g. So vy squared is 0, because that is equal to 0, minus 2 times g times y final is 0, y initial was plus 1.5, so I'm doing 0 minus 1.5. So what you don't want to have when you do these things is the square root of a negative number, which is kind of easy to end up with. If you end up with the square root of a negative number, it usually means you've done something wrong in your setup. So vy squared is equal to, the negatives cancel here. You get negative 2 times 9.8 times negative 1.5. And then, so these negatives cancel. And you get vy is equal to, and this is another interesting thing, is that when you do have the square root of a positive number, there is a plus or minus that comes out in front of the square root. So when you have x squared equals some constant, there's two possible solutions for x. It's either plus or minus that square root. So then you have to choose based on physics which is the correct answer. So in this case, is it plus or minus that's correct? Minus. I heard some people yell, yeah, in this case, it's minus that's correct, because we know it's going down just before it hits the ground. So we choose the negative solution here. So that's good. So you say that Vy is equal to negative 5.422 meters per second. Okay. Everybody see how we did that? And then part B, it says calculate its velocity just after it leaves the floor on the way back up. So what we're saying is that there was free fall with this, gravity is negative 9.8, that's the whole acceleration. Then it hits the floor and there's some bouncing part when it's in contact with the floor. And we're going to skip that and come back to it later. After it leaves the floor again, it's now a projectile again. So it's again accelerating like with the minus 9.8. Or decelerating, I guess, slowing down until it reaches some new height final height of 1.1. So we're just going to do the whole thing again, but this time say that it starts down here with y initial equals 0, and it has some plus v initial, which we don't know, which we're trying to find that, and it goes up here and then stops, v final equals 0 at the maximum height. That's a trick. If I know that something reaches some maximum height of 1.1 meters, y is equal to 1.1 meters, then what I know by that is that if it's maximum height, it went from positive to negative velocity, so that must be where the final velocity is 0. So that's important. So then, again, I think we're going to use equation 3.40, Vy squared, but the setup is a little different now. V initial y squared minus 2 times g times y. Same equation, but now it's different. So you get 0 is equal to V initial y squared minus 2 times g times 1.1 minus 0. So V0 squared is 2 times 9.8 times 1.1. So again, there's this plus or minus square root of 2 times 9.8 times 1.1. Do you think you'll choose the plus or the minus in this case? So after it bounces, is it going up or down? Going up, so I think we'll just choose plus. Let's choose. So there's nothing in the math here that tells us that it should be going up. It's just the physics. We know after it bounces it's going up. So we just choose the positive solution. And then part C says calculate its acceleration during contact with the floor if that contact lasts 3.5 milliseconds. So what's really important here is that you're trying to find the acceleration. The acceleration is not 9.8. And that's because there's this big giant force from the floor kind of while the tennis ball is getting squished by the floor. And it's reversing its velocity. So part C looks like this. You've got, I guess, just before the collision, I would say that maybe V0y is negative 5.422 meters per second. This is from part A. So we use our result from part A, and then just after the collision, you've got from part B, we just figured that out. I'm going to call that the final is equal to plus 4.643 meters per second. And we know that this all happened in t is equal to 3.5 times 10 to the minus 3 seconds. And we need the acceleration. Acceleration is question mark. So I'm going to use the simple equation, Vy is equal to V initial y plus ay times t, and solve for acceleration. So I get Vy minus V0y is equal to a times t. Acceleration is the change in velocity divided by the time. So you get 4.643 minus negative 5.422. So that's going to be adding those two numbers and divided by 3.5 times 10 to the minus 3. And I get something huge, 2876 meters per second squared. So while the tennis ball is hitting the ground and there's that huge force from below, it's actually accelerating at plus like almost 3,000 meters per second squared. This was actually from last class. A wind of 50 meters per second blows from east to west. So the first thing I'm going to do is kind of draw a bird's eye view here. Never eat shredded wheat. And draw, let's define, I guess. Plus y is up and plus y is north and plus x is east. So in that case, the velocity of the air relative to the ground, so I would say A is air, G is ground. What the wind means is that the velocity of the air relative to the ground in the x direction is negative 50 meters per second, because it's from the east to the west. It's going towards the west. Makes sense? That's how I'm interpreting that. And it says, an airplane heads straight north with an airspeed of 200 meters per second. So what I think that means is that like the airplane is pointing with its rudder or something straight to the north. And so I kind of think of the pilot as being in this universe where it's just air. And there might be some ground down there moving around, but since it's so far, the pilot doesn't really care too much about the ground. Everything the pilot is doing is relative to the air. So what that means is that the velocity of let's call P is the plane. The plane relative to the air is in the y direction only. Also just say that V A G Y is equal to 0. The plane relative to the air in the y direction is going north, so plus 200 meters per second. And then it says, what is the direction that the airplane flies relative to the ground? So what we're looking for is we want VPG. And so the way I would draw it here, I would say VPG vector is equal to, PA plus VAG. So I would draw it kind of like this. Here's your 200, here's your 50, and this is the velocity of the plane relative to the ground. So it's getting kind of thrown off to the west by some theta. And the question is, what is the direction? So I would say theta is equal to tan to the minus 1. This is a right angle triangle of 50 divided by 200. I'm using opposite over adjacent there for tan. Okay. So when I plug that into my calculator and I have it in degrees mode, I've got 14.0 degrees west of north is that angle. So the plane, even though it's pointed north, the wind is blowing it a little bit west. This question says, same thing, a wind of 50 meters per second blows from east to west, so the velocity of the air relative to the ground is negative 50 meters per second, so similar definitions. The airplane has an airspeed of 200 meters per second, but they want to head towards this airport, which they know is straight north. So the question is, what that means there, an airplane wants to head north relative to the ground. What is the direction that the pilot should aim for? So this is a little bit more what they probably do, right? Is that they care about getting to a certain airport, and they know it's straight north, so they have to compensate for the air. So you would say here that VPG is north. So again, I would set it up, so I would say, it sort of looks like this now. Here's your 200, here's your 50, and here's your VPG. And then here's your theta. That's the angle, I think, and this is the right angle triangle like that. So it's the same equation I'm using, but now I'm just setting it up this way. Remember, this is the velocity of the plane relative to the air. This is the velocity of the air relative to the ground. So they have to add up to be something north. And in this case, so now I can do, the thing I know is the hypotenuse now. So I need to go, that theta is sine to the minus 1 of 50 over 200. So this is actually 14.04, and this one is theta is equal to 14.48. It's kind of weird. They're very close, but they're just a little different because I'm using sine to the minus 1 instead of tan to the minus 1. And this one also is east of north.